Last week we talked about what was photoelectric emission. So last week we mentioned photoelectric emission, which is actually just emission of electrons on the surface of a metal when it is exposed to electromagnetic radiation of sufficiently high frequency. So what photoelectric emission actually proved to you was that if you want to explain the phenomenon of photoelectric emission, it cannot be explained by assuming that EM radiation is a wave. It can only be explained by assuming that EM radiation is actually particles called photons. So photoelectric emission itself tells you that wave can behave as particle, right? Photoelectric emission tells you that wave can behave by particle because the observations that you see there can only be explained by assuming that EM radiation is a particle in the first place. You cannot explain it by assuming that it is a wave. Okay, so if you say that a wave can behave as a particle, can a particle behave as a wave instead? Can it behave in reverse? Can a particle actually behave like a wave? So the answer is yes. Okay, a particle can actually behave as a wave. And when you are interested in talking about waves, when you're saying waves, have a quantity called wavelength, and then waves can exhibit certain phenomena such as interference or diffraction. Okay, so now before I go to the part of explaining why the part where a particle can behave as a wave, you need to know that for wave, there are certain things that you tend to associate with a wave. A wave normally has a wavelength, okay? And a wave can also exhibit certain phenomena such as interference or diffraction. Interference and diffraction are only specific for waves, not particles. So here we will tell you that particle can behave as a wave, and if you're saying a particle can behave as a wave, and you're interested in talking about its wavelength, that one is described by de Broglie's. Okay, the de Broglie wavelength is actually the wavelength associated with a particle that is moving. Okay, so you want to describe a particle that's behaving as a wave, you will tend to relate it to de Broglie equation, or here the de Broglie wavelength, which tells you that if you have a particle and you're saying that it's behaving as a wave, the wavelength of that particle is equals to the Planck constant divided by your momentum. Okay, so that part is okay. Now, how do you specifically prove that a particle is actually now behaving as a wave? I told you that a wave can exhibit interference pattern, right? Or diffraction. So when you were talking about interference and diffraction in AS physics superposition, we talked about this before, right? The effects of interference and diffraction. Remember, if you had say diffraction grating, you say you have a diffraction grating, and then you had a screen behind here like this. If you say that you shine a beam of light here to the diffraction grating, this is a diffraction grating. If you shine a beam of light to your diffraction grating, what happens to the beam of light was that the beam of light will actually diffract, it will interfere with each other, and then it will give you these beams, right? It will give you these lines here, and then over here, you will see those dots. Okay, so your light, when it passes through the light here, which we should assume as behaving as a wave, when it passes through the diffraction grating, there is diffraction at the diffraction grating, and then there is also interference when the waves have diffracted, isn't it? So this part here is where you see your waves are diffracting, they're spreading out after passing through your slit, and then over here you have your interference. So specifically what you saw was that there is what you call an interference pattern here, right? So you know that this interference pattern came about because the waves diffracted and superposed with each other. Superposed as in interference, superposed with each other, okay, which is due to interference. Okay, so beam of light hits diffraction grating, it diffracts. When the waves diffract, they interfere with each other, giving you the resultant interference pattern here. So it's correct to say that you get this pattern here because the waves were diffracted and then they superpose with each other, right? So this one is one of the characteristics of wave that you expect to see when you pass it through a diffraction grating. It will form an interference pattern. So like now, if I tell you that a particle can behave as a wave and the wavelength is associated with this, if you want to go one step further and prove that the particle is behaving as a wave, the particle must exhibit interference pattern also. Okay, so you need to be clear that interference pattern here came about because of diffraction and interference, and these two can only come about because whatever it is that passed through the diffraction grating is actually a wave. Only then can you get this. So if you want to prove that a particle can actually behave as a wave now, you will have to make use of something called electron diffraction. Okay, electron diffraction proves to you that a particle can behave as a wave. Okay, so electron diffraction tells you that particle can behave as a wave. Now, electron itself is a particle. Diffraction is something that you associate with wave. Okay, so we'll be clear here. We are talking about electron diffraction here. So what is actually electron diffraction? It's just something like this. In your case here, the case of the diffraction grating, I think you guys can understand this part here. Now, for electron diffraction, if I refer to this diagram here, it's actually akin to something like this. What we're telling you here is this. You have an electrode that is being ejected from the cathode here. What you do is that you run current through this apparatus here. The filament will heat up and then after that you emit electrons. Okay, but this side is negatively charged, is your cathode. This one is positively charged, is your anode. So what will happen is that once the electrons are ejected from the cathode, because there's a potential difference between your cathode and anode here, your electrons will accelerate. It will achieve a certain velocity. And then if there's no other forces acting on it, it will just keep on moving straight. So you have an electron that is being accelerated in a straight line here. What you do is that you place a graphite film in the path of the electron. Okay, you place a graphite film in the path of the electron. So what you expect to see is that once the electron passes through the graphite film, you will see that behind here, if you put a phosphorus screen, you will see some sort of pattern, some form of concentric rings, okay, on the phosphorus screen. That one is your electron, is your diffraction pattern, is your interference pattern here, okay? So the fact that you can see electron diffraction pattern and interference pattern on the screen proves to you that your electron is actually behaving as a wave. Your particle is behaving as a wave. So that's the significance of your electron diffraction experiment. You can see that you form concentric rings here on the phosphorus screen. This is actually your interference pattern that came about from your electron diffracting at the graphite. Okay, so your graphite here is actually akin to a diffraction grating. If you're talking about the structure of a solid, say graphite, you know that the structure of a solid is such that the atoms are arranged in a crystal lattice structure. So if this one is, say, your graphite film, and I tell you that your atoms are arranged in a regular pattern in a crystal lattice structure like this. The gaps between the atoms is actually akin to your slit. You see, the gaps between the atoms here form a line, right? This one, this one, this one, this is a set of slits, right? If you look at it, because your atoms are arranged in a regular pattern like this, you can see that there's something that looks like a slit here. Okay, there's an opening here, regular opening here. So this one is akin to your slit. So you have one set of slits in the vertical direction. You also have one set of slits in the horizontal direction. So your graphite here actually has something like it has something like slits in its structure that is both horizontal and vertical. Okay, actually there's also another pair of slits in a different direction, in the z direction, because your solid is 3D by right. So you would have slits in the x, y, as well as z direction. So once your electron that is now behaving as a wave, so this is your electron that's behaving as a wave, passes the graphite solid here, it will diffract in all the different directions. It will diffract vertically, horizontally, and into the plane of the paper. And then what you see at the end, if you have a phosphor screen here, is that you see a form of concentric circles. That one is telling you your interference pattern, which came about due to the electrons diffracting over the graphite solid in the first place. Okay, so that is the gist of this. How exactly does electron diffraction work? Why, where, what you need to do, etc. You don't need to know that much in detail. All you just need to know is that if you are asked about a particular thing that you can do to show that particle can behave as a wave, just recall that you can show it by using electron diffraction. What they're actually doing now is that they are accelerating an electron through a graphite field. The electron now behaving as a wave will diffract over the graphite and form interference pattern in the phosphor screen. If you can see interference pattern here, it means that your electron was behaving like a wave, because interference pattern can only come about when you have diffraction. And when you have diffraction can only occur if you have wave behavior. Okay, so that is what you just need to know. All right, so just remember these two things. If you are asked to show what can be used to show that wave behavior as particle, photoelectric emission. Conversely, what can be used to show that particle behaves as a wave, use electron diffraction. Okay, so that part is fine. Then after that, we just go on to your question. Go and have a look at your worksheet. Have a look at your worksheet. Page 1. Have a look at your worksheet, page 1. Go to page 1 of your worksheet. Page 1 of your worksheet. This is June 15 P41. Not question numbers, this is question 8. So you have a photon of wavelength 6.5 times 10 power minus 12 meter that is inserted on an isolated stationary electron as illustrated in figure 8.1. The photon is deflected elastically by an electron of mass. The photon is deflected elastically by the electron of mass ME. The wavelength of the deflected photon is 6.84 times 10 power minus 12 meter. You have a photon, it hits the electron, it got deflected. That's what the question is just basically telling you. They're asking you right now, for that photon, what is the momentum of that photon? Okay. Now your photon here is a particle, right? And then after that, they ask you to find out the momentum of that photon. So now your particle here also has a wavelength associated with it. So when you're talking about particle and then you notice that you have a wavelength associated with it, someone tells you you can use the Brown wavelength, the lambda equals to h over p. So here you have the values of your wavelength, you have the values of Planck constant which you can get from your data sheet. You sub those in, you can find out straight away what is the momentum of your photon. Alright. You have to use the Brown wavelength here because this is a particle and there's a wavelength associated with it. Alright, then be careful about the terms here. Incident photon. They're talking about the photon before collision. Don't go and use the values for deflected photon. Deflected photon is after collision. They don't want this. They want the incident photon, the photon before collision. So just get that one out. You get your answer as P 1.02 times 10 power minus 22 Newton seconds. Alright. We'll just get that one sorted out first. Right, so if you have done that, we'll move on to the next one. Then the next thing here is that for that incident photon here, calculate the energy. So energy of photon by Brown, you should know that is equals to E equals to hc over lambda. It's either E equals to hf or E equals to hc over lambda. So same thing as before, just sub everything in, you get the answer is 3.06 times 10 power minus 14 joules. So this is a simple application of the equations. So just get it done. Okay. So if you have that done, then after that we go on to the next one. Now they told you the angle theta through which the photon is deflected is given by this expression, where change in wavelength is equals to Planck constant divided by mass of electron multiplied by the speed of light multiplied by 1 minus cos theta. Okay. Now calculate the angle theta. This one doesn't really require much thought to it. You just need to sub in the equations and the values to the equation, that's all. You know the mass of electron, 9.11 times 10 power minus 51. You know the speed of light in vacuum. You know the change in wavelength. The change in wavelength is between this and this. Just get the difference. And then you get your angle. Just make sure your calculator angle, your calculator is set to degrees, not radians, when you want to find the angle. You get the answer as 30.7 degrees. Okay, right. So that one is fine. Then they will ask you to look at part 2. Part 2 is the state and explain question. So This one actually no problems on. Alright, part 2. Use energy considerations to suggest why delta lambda must always be positive. Now, they say use energy considerations. When they say use energy consideration, there's this thing you need to be aware of. Your photon is moving here. It collides with your electron. Then after collision, your electron probably will move this way, which is not shown in your diagram. But what they show in the diagram here is that your photon moves this way, right? Okay. So when your photon hits your electron, your electron was originally stationary. Okay. When your photon hits your photon got deflected. By right, your electron would have also moved. Okay. It definitely must have moved. The next question will tell you why it must have moved. But now I just tell you first that when your photon hits your electron, logic will tell you that your photon will move one side, electron will move another side. It cannot be that your photon hits the electron and the electron itself remains stationary while the photon got deflected away. No, it cannot be possible. The electron must also have moved after the collision. So now this is the case before, and this is the case after. Now, if you're talking about energy conservation, because they ask you to use energy considerations here, what can you actually say from here? The energy of your photon initially must be equals to the, maybe I just rewrite this. See, when your photon hits the electron, before the collision, what's the total energy? The total energy is just the energy of the incident photon, right? The electron itself being stationary does not have any energy. So you can say that the energy of your incident photon is equals to the energy of the deflected photon plus energy of the electron after collision. Okay, so what you can say from here is this: your before and after the collision, this is the conservation energy applied for it. The energy of your incident photon is actually split between the energy of the deflected photon and the energy of the electron itself. Is shared with these two objects after collision. Okay, so from there, what can you say about your energy of your deflected photon? You see the energy of your deflected photon is actually energy of your incident photon minus energy of your electron. It's actually going to be less than before because it is incident energy, the energy of your incident photon minus all the energy of your electron, isn't it? Whatever energy of photons that you get here is going to be less than before. So E is equals to hc over lambda. If your energy of photon drops, your wavelength would increase. Okay? So when they say delta lambda, why is it that delta lambda must always be positive? If delta lambda is positive, that means the final wavelength is more than the initial wavelength, right? That means lambda must have increased. So if you say that lambda must have increased, why must the lambda have increased here? It is explained based on looking at this. Okay, based on energy conservation. You will have to say that your deflected electron actually has energy after collision. The energy is actually derived from the incident photon. So your deflected photon would have less energy and thus a longer wavelength. So if you have a longer wavelength now, that means your lambda final is more than the lambda initial. Therefore, the change in lambda must always be positive. That's what this one is trying to tell you. Okay, so please copy that. You can just say this anti-deflected electron has energy after collision. This energy is derived from the incident photon. So therefore, your deflected photon will have less energy, and thus it will have a longer wavelength. Therefore, delta lambda is always positive, because your lambda here after collision must have increased. So your lambda here has increased, your change in lambda is positive. Okay. So if you're okay with that, then you can move on to page 3. Alright. Okay. So if nothing else, go to page 3. The one is June 15, P42. So this one I will just go on. June 15, P42. Question 6. Now define what is meant by a photon. This one you should know by now that it is a packet of energy of electromagnetic radiation. That's what photon actually is. Okay, it's a packet of energy of electromagnetic radiation. This one is 2 marks, so it will just be sufficient if you just write a packet of energy of electromagnetic radiation, where first mark is for packet of energy, second mark is electromagnetic radiation. If it just so happens that you are unlucky or lucky that you get a 3-mark question for definition of photon, this is 3, you will need to add this one. You will need to specifically tell us how to calculate the energy of a photon. E is equals to HF. But please make sure you also define the variables that you use. Okay, in the event this is a 3-mark question. I think it came out before in the older past years, that's why I made a note here. Okay, so this part is fine. If you look at part B is actually the exact same diagram as before, alright, but the context of the question has been changed. You have an X-ray photon of energy 3.06 times 10 power minus 14 joules that is incident on an isolated stationary electron as illustrated in figure 6.1. The photon is deflected elastically by the electron through an angle of theta. The deflected photon now has a wavelength of 6.8 times 10 power minus 12. Now on figure 6.1, draw an arrow to indicate the possible initial direction of motion of the electron once the photon has been deflected. So just now, in the previous question, I mentioned to you that when your photon hits your electron, logic will tell you that your electron definitely must move, right? It cannot be your photon hits your electron, but then the electron remains as it is, but only the photon got deflected. That's just not possible, right? Your electron definitely must have moved. But how would it move? In what direction would it move? Again, common sense will tell you your electron definitely must have moved downwards, right? If I just show it to you now, what was mentioned was photon moving this side hits an electron. This is before. After collision, photon move this way. By right, your electron after collision must also move this way. Common sense will tell you that. But if you really want to know why must it move downwards rather than here or rather than here, the easy thing is to use conservation of momentum. If you remember your 2D momentum in your AS, 2D conservation of momentum, you know that sum of initial momentum in x direction must be equals to sum of final momentum in the x direction. Likewise, sum of initial momentum in y direction must be equals to the sum of final momentum in the y direction. This is 2D momentum, conservation of 2D momentum. So the thing here is this, the one that you are really interested in is this. I can talk about the horizontal momentum being conserved. I can also talk about the vertical momentum being conserved here. I am more interested in the vertical momentum because you see here, this one was moving horizontally. This is not moving. Your initial momentum vertically is actually 0. If you still need to satisfy conservation of momentum, your final momentum after collision in the vertical direction must also still be 0 because you need to follow conservation of momentum here. So the thing here is this, because your your photon here has moved in this direction, you know that it has a component of momentum in this direction and in this direction. Okay, so you know that your final vertical momentum must be 0. Okay, but now you have a vertical momentum here, so it follows that something else must be balancing off this vertical momentum so that it becomes 0 in the first place. That can only come about if your electron is moving at this angle, so that you have a component here and here. This one will balance this one so that it becomes 0. You cannot have your electron moving in this direction, because if you do that, the component will be like this and like this. So this one is in the same direction as this one. They will never become 0. So this is out, straight away out. Okay. So the only sensible one will be this one. All right. That's a proper explanation for it. But common sense will tell you it's just this direction without talking so much about that. All right. Then part 2. They ask you calculate the energy of the deflected photon. Now this one, be careful. They're asking you energy of deflected photon, not incident photon. The question before this asks you energy of incident photon. This one is asking you about deflected photon. It means the photon it means the energy of the photon after collision. You use the wavelength, then you use back hc over lambda, you get back your answer. 2.93 times 10 power minus 14 joules. Okay. So that part is fine. Then we'll move on to your bottom one. Now then find out the speed of the electron after the photon has been deflected. Okay, so find out the speed of the electron after the photon has been deflected. So this one you can use back conservation of energy, following away the method similar to what I described to you just now. Your photon comes here, your electron is here. This is before. After collision, your photon moves here, whereas your electron moves here. So it will be correct to say that the energy of your incident photon is equals to the energy of your deflected photon plus the energy of your electron, right? The energy of your electron is actually the difference in the energy of your incident photon minus deflected photon. Okay, right? Maybe you want to write this like energy of incident photon, energy of deflected photon. Okay. So the energy of your electron is actually just the difference in energy of your incident photon and deflected photon, which actually kind of makes sense, right? Because whatever energy your photon has lost after the collision must have been the energy gained by your electron. In other words, you can just think of it as this: energy lost by photon is equals to the energy gained by electron. Some people tend to think it as this way. It's also fine because it's still derived from this way. It's still derived from this in the first place. Okay. So once you have gotten the fact that your energy of electron is just actually the difference in your incident photon and your deflected photon, you can then work out further what is the speed. Your electron here is in the, your energy of your electron here is in the form of Ke. This is in the form of Ke, half mv squared. So what you do is you find the difference in the photon energies, that is the energy of your electron. The energy of your electron is also subsequently half mv squared. So then after that, you just make use of that equation, find out what is your V. You also know the mass of your electron. It is 9.11 times 10 power minus 31, which you take from your data sheet. So find out the answer is 5.34 times power 7. Okay, so this one should be fine. Alright, so if this one is fine, then you go on to the next one. They're asking you to explain why the magnitude of final momentum of electron is not equal to the magnitude of the, it's not equal to the change in magnitude of momentum of the photon. Why is that so? Because you see here what you have done here was that you said that the energy of your electron is equal to the change in magnitude of the energy of the photon. Right? You see from here the energy of electron is actually equals to the change in magnitude of energy of the photon. So this question here subsequently was kind of referring to this, and then they ask you, if I want to find out the final momentum of the electron, why is it not equal to the change in magnitude of the momentum of the photon? Can I say that the momentum of the electron here is actually just the difference in magnitude of the momentum of the incident photons? Can I just say that? The answer is no, because here you already know that momentum is actually a vector, isn't it? Momentum is a vector, so energy here was fine. If you say the energy of electron is actually the difference in energy of the photon, it's actually just the difference in magnitude of the energy of the photon, that one has no issues here because energy is scalar. Direction does not need to be taken into account. But momentum, on the other hand, is a vector. So in your case here, direction has to be taken into account. Now the easy way to look at this is by looking at this. The easy way to understand this is to consider this now. If I give you two vectors, 3 Newton and 4 Newton, the resultant is actually going to be 7 Newton, right? Because it is just 3 plus 4 Newton added up together. Write this. If I have two vectors in the same direction, 3 Newton, 4 Newton here, the resultant is actually just going to be 3 plus 4 equals 7 Newton. This one I can just add the magnitudes together because they're in the same direction. If say for example they're not in the same direction, this one is 3 Newton, this one is 4 Newton, the resultant is actually going to be 3 Newton, 4 Newton, 5 Newton, right? Because this one is square root of 3 square plus 4 square. So this one here is not the same as you saying 3 plus 4 equals 7 Newton, right? This one is definitely out, right? In your case here, if I have 3 vectors in different directions and want to add them up, it's not as simple as saying I can just add up the magnitudes together and that's the result, and that is wrong. You have to, if it's right angle, you have to use Pythagoras theorem to get something like this, right? So here you bring over the same concept. Because momentum here is a vector, you cannot just simply consider magnitude because you have to consider the directions also. Okay? You can just say firstly momentum is a vector quantity. Then after that, if you want to simplify the last two sentences, you can just say that direction also has to be considered, not just the magnitude. That one will be fine. Okay. So that is fine. Then you go to page 22. This one is the last one before I need to move on to the next chapter. Not next chapter, the next subchapter. You're fine with that? Go to page 22. Hey, sorry, not page 22, page 23. Actually. Hey, page. Huh? 22, 23. Okay, never mind. Just go to page 22. Right. You are November 17 P41. Alright, so let's just go through that. And this one is question 11. Okay, step one is meant by photon. I'll just skip that because that one is already something I've already talked to you about. Packet energy, electromagnetic radiation. Now the other one here is indium. Indium 123 is a radioactive particle. A nucleus of indium 123 emits a gamma ray photon of energy 1.1 mega eV. Therefore, determine for this radiation the frequency. So this one nothing else to this. You just say that E is equals to HF. Because they give you energy and one frequency, you know that you need to use E equals to HF. So just summing all the values and you get a frequency as 2.65 times 10 power 20. So that's one just simple application of the equations to do. And then the last one here is find out the momentum of the photon. Okay. Find out the momentum of the photon. The momentum of the photon here is just simply P is equals to H over lambda. Okay, your photon here is a particle. You want to find the momentum, but you also know the photon also has a certain wavelength here, which you can find. You can use P equal, you can use lambda is equals to H over P. Okay. Lambda is H over P. So P is H over lambda. And then lambda is in turn C over F. Because C is equals to F lambda. Lambda is C over F. So you sub that in. You get this. Then you find out your momentum. Okay, 5.86 times 10 power minus 22 Newton second. Right. There's this one thing problem here. I should highlight that. D is equals to HF. Then P. Then lambda. Okay. Yeah, never mind. Don't bother with what I write here. Okay. So you get your momentum as 5.86 times 10 power minus 22 Newton second. Alright, then that one should be fine. Okay. So then after that, they tell you your indium-123 nucleus is stationary before emission of the gamma ray photon. Use your answer in B2 to estimate the recoil speed of the nucleus after emission of the photon. Okay. So based on what they've told you here, indium-123 nucleus is stationary before emitting the gamma ray photon. Okay. Find out what is the recoil speed of the nucleus after emission of the photon. This one you have to use your conservation of momentum. If before this you have indium-123, which is stationary. This is the before case. After some time, your indium-123 emits a photon, and the photon is moving away. So what is the recoil speed of this indium-123? Now this one here, you need to use that conservation of momentum. Now your initial momentum is actually 0 here, right? Your photon is not yet present. Your indium nucleus is stationary. Your initial momentum is 0. If you want to follow conservation of momentum, your final momentum must also be 0. So now think about it. If your photon, maybe I need to write this. If your photon is now moving like this, if your photon is moving like this with a certain momentum, your indium-123 must be having a momentum equal and opposite to your photon, so that your final momentum is 0, isn't it? Because you need to follow conservation of momentum. So here you can come to the conclusion that momentum of indium-123 and photon are equal and opposite, so that the final momentum remains 0, so that conservation of momentum is still obeyed. So this part here was actually basically just showing that lah, but you don't really need to show this part. You just needed to know this fact, that the momentum of your indium nucleus is actually equal to the momentum of your gamma ray photons itself. Your momentum of your gamma ray photons you've already found. You want to find the momentum of your indium nucleus, the mass is 123U. This multiplied by speed will give you is momentum. So eventually you get your speed 2.87 times 10 power 3. Okay. So that part is fine. Then after that you can go on to page 21, which is the page before this. Okay. So there's something here that has been bothering me for some time. Lambda is H over P. Yeah, no, it's H over lambda. So lambda HC P. Yeah, this thing here I think I better just highlight to you. There's this little thing here over in the previous question that I say momentum is actually equals to E over C, right? In case you're wondering where that thing even come from, it came from this here. You know that the broad wavelength lambda is H over P. You also know that energy over photon is H over lambda. If this one you sub inside here, this becomes this. The H will cancel off, giving you momentum times C. So this one here is actually this one. Okay. This one was not written inside your notes, but sometimes you see in your marking scheme when they want to find momentum, they sometimes use this form of the equation. Just know that it's actually from these two combined together, that's all. Okay. So that one assuming there is that big on the issue. Go to page 21. Alright, go to page 21 if you're okay with that. Page 21 is question 11. This one is doing 17p for 2. Okay, so question 11. Right, so nothing else, go back to this. Now, for question 11, page 21, you have an electron that has a charge of negative Q and mass m. It is accelerated from rest in a vacuum through a potential difference of V. Show that the momentum P of the accelerated electron is given by this equation. P is equal to square root 2 mqb. So what you just need to do here is this. Now, based on what the question told you, you have a vacuum here. Maybe I shouldn't write it inside. You have a vacuum and you have an electron that you accelerate from rest. Okay, 0 meter per second that you accelerate from rest in the vacuum through a PD of V. So in your vacuum here, you have a potential difference of V. Alright. So the thing is that when you accelerate your electron through the vacuum here like this, you eventually reach a speed V here. So show that the momentum P of the accelerated electron is given by this. So based on what you have here, the first thing that will come to mind here is that you see there's changes in energy here. Here to here from 0 meter per second to speed V, there's changes in KE. There's increase in KE. And your electron here is actually inside an electric field. How do I know that your electron is actually inside an electric field? Is because here they tell you in this region here, there's a potential difference of V. So that means this one is an electric field already. You can only have electric field if you have potential difference. Okay, so from here you know that yes, there's changes in K. There's also the fact that your electron is moving inside an electric field. So if you have a charge moving inside an electric field, you know there's a force, you know there's a distance moved, you know there's work done. So in your case, your work done on isolated charge in an electric field is QV, right? So work done is QV. The change in KE here is half mv squared minus 0. Okay, so this one here is actually the work done on isolated charge in electric field. Remember this from your electric field chapter. W is equals to QV. QV here, V here is actually your potential difference. Okay. Now you can say that by conservation of energy, whatever work was done inside your isolated charge is used to change the KE of the electron. So hence you get this. Work done is equals to change in KE. You can also say this loss in electric potential energy is equals to gain in kinetic energy, but I think it's more sensible if you think of it in this way. So your work done on isolated charge in electric field is QV. A change in that one is used to change your kinetic energy, then you get this. Alright. So you get QV is half mv squared. Then this part onwards, whether you want to copy it or not, I do not know, it's up to you, but I think I better just show you another different way of doing this. This part here, because you want momentum, right? You say that since P is mv, V is equals to P over M. So this one, this whole thing here, you sub inside here straight. You have QV equals to half mv V, right? This one is QV half P P over M. Then you will get QV 2P squared M. So your P is actually 2MQV square root. Okay, this is another way of deriving it. I derive it in this manner. This one is another way of deriving it where I just multiply both sides by mass. Then I get this. But some people don't like this method, some people prefer this, so it's really up to you. And the other thing I need to highlight to you is this. This V and this V are not the same. Don't simply cancel them off. Don't go and see, oh, this one is V, this one is V, so this and get this cancel off. So it becomes Q equals to half MV. They are talking about two different things entirely. This V here is potential difference. This V here is speed. They're not the same V. Please don't cancel it off. Alright. So this one is fine. Then you can go and have a look at the other page. Not the other page, sorry, the next question. Now, they tell you that the potential difference V through which the electron is accelerated is 120 volts. State what is meant by the de Broglie wavelength. Okay, so as I mentioned to you, de Broglie wavelength is just simply the wavelength associated with a moving particle. Right? One mark for saying wavelength, another mark saying is associated with a moving particle. That's all there is to it. Then they ask you to calculate the wavelength of the electron, the de Broglie wavelength of the electron. You know that you can use lambda equals to h over p, but you see from here you already find out what is p in the first place, so you sub in p inside. Then the rest of it you just sub in the values and you will get your answer 1.12 times 10 power minus 10 meter. Alright, then you get your answer there. So just get that done, and then you go on to the other one. Then the next one will be this one. Okay. The next one will be this one. Okay, now the separation of copper atoms in a copper crystal is approximately 2 times 10 power minus 10 meter. By reference to your answers in B2, suggest whether electron diffraction could be observed using a beam of electrons that have been accelerated through a PD of 120 volts and then incident on the thin copper crystal. So right now, what they're telling you is that you have an electron that you are trying to accelerated, and you're trying to pass it through a copper crystal. They're asking you whether would you observe electron diffraction here. In other words, what they're telling you is this: you have an electron beam here, and then this one here is your copper crystal. And then say this one is your screen. They're asking you right now, can electron diffraction be seen? Do you get the pattern of concentric circles here? Now, before I go to that, I mentioned to you, electron diffraction is just basically your electron behaving as waves, and then it diffracts, and then it interferes with each other, and then it gives you your interference pattern, right? Alright. So remember, when you want to have interference pattern, your waves must be diffracting significantly in the first place. So the thing here is this: if you want to see some sort of diffraction pattern or interference pattern, the waves must be diffracting significantly. And you know that if your waves were to diffract significantly, there's a relation between the wavelength and the opening of your gap, or opening of your slit. Last time in AS, we often told you this, right? If wavelength is comparable to size of opening, diffraction is significant. How to spell significant really? Significant and diffraction is significant. Okay, meaning to say this one is your wave and then this one is your opening. If this one, the opening here is comparable to your wavelength, you expect to see significant diffraction. This was the little thing that I was talking to you guys about last time in AS, right? If wavelength is comparable to size of opening, the diffraction will be significant. Okay, so now you know that in electron diffraction, your electron beam here is behaving as a wave. Once it passes through the copper crystal, it diffracts. And then after that, your screen here will show the diffraction pattern or the interference pattern. If you want to see your diffraction pattern here, your diffraction here must be significant in the first place. So how do you ensure that you have significant diffraction? You have to compare the size of your opening in the copper crystal and your wavelength. So this one was the first statement. Significant diffraction occurs when wavelength is comparable to separation of the atom. Since the wavelength in B2 is comparable to 2 times 10 power minus 10, therefore the electron diffraction will occur. Now when you say comparable here, you can just think of it as same order of magnitude. Right, so when you're talking about the copper crystal, the copper crystal will be something like this. As I mentioned to you, your copper crystals, the atoms are arranged nicely. When they say the separation here, it's more like this one. This is your so-called slits. And this one is the size of your slit, which is 2 times 10 power minus 10 meter. And your wavelength of your electron is 2 times 10, 1.12 times 10 power minus 10. You see this one and this one, same order of magnitude, right? So you can say that there is significant diffraction. Alright? You want to see the diffraction pattern? Your waves must diffract significantly. You want your waves diffracting significantly, you need to have the wavelength comparable to the separation of the atoms. That's the gist. Yeah. Now let's something P42. You have a metal surface that is illuminated with a light of a single wavelength lambda. On figure 10.1, sketch the variation with lambda of maximum kinetic energy, Emax of electrons emitted from the surface. On your graph, mark with symbol lambda naught the threshold wavelength. Okay, so what is actually happening here? You have metal surface illuminated with light of wavelength, and then you have emission of electrons with maximum kinetic energy. This one you know is talking about photoelectric emission, which is Hc over lambda equals to Ke max plus 5. So this one I mentioned to you, Ke max Hc over lambda minus 5 would give you this equation. It will give you this equation. And then the resulting graph will look like this. K max over 1 over lambda. If this one you rearrange it properly again, K max HC1 over lambda minus 5 will give you this graph. Straight line graph with negative y-intercept. Okay, this one is this right. Okay, what they're asking you right now is to draw E max versus lambda, not Emax versus 1 over lambda. If it is Emax versus 1 over lambda, this is the graph shape that you should give. But this is not 1 over lambda, this is lambda itself. So there's something here that you need to change. Now, there's something else here that I need to kind of highlight. You remember that in maths, if you get y inversely proportional to x, your graph shape will look like this. Okay, sorry. Your graph shape will look like this. Cannot draw the curve properly, but I'll try. This one and this one will never touch, right? The axis will never touch because these two are your asymptotes. The axis will never touch, okay? But say if, for example, I give you something else, where I tell you y is also inversely proportional to x, y is inversely proportional to x, but then I tell you that this one is minus with something, say maybe minus with a value minus 5. This graph shape here will now automatically be something that looks like this right now, right? You will still have the same general shape. Originally it was like this, but what will happen is that your new graph shape will look like this now. It's been shifted down by 5, right? Minus 5. Okay, so the thing here that you realize is that this part here will still be your asymptote, but now here you have a x-intercept. Okay, so this one here, in general, in concept, this is what it looks like, right? Now, if you look at this equation now, Ke max is actually inversely proportional to 1 over lambda, right? So you expect the graph of Ke max versus lambda to become like this, where you have both asymptotes here and here. But notice that there's a minus something here. There's a minus lambda here. So this part here now becomes Ke max proportional to 1 over lambda minus 5, say for example. So this graph shape here must have been shifted downwards. So your Ke max lambda, originally it looks like this. It would now have to be shifted downwards, so that you still have asymptote here, but then now you have an x-intercept. Previously, these two would have been your asymptote. They will never touch. But once you have something minus or something here, this one will shift down. You will still have your asymptote on your y-axis, but your x-axis no longer has an asymptote. You will have an x-intercept instead. So therefore, your graph shape becomes like this. Okay, your asymptote is still here, but here you will have an x-intercept. Okay, what is the x-intercept here? The x-intercept is your y0, because you remember that I told you that lambda is actually your threshold wavelength when E max is 0. At threshold wavelength, your electron does not have kinetic energy. The energy supplied by your photon is just enough to remove electron from the surface of the metal. Okay, so this is your actual graph shape. You need to make sure there's an x-intercept here and there's a asymptote here. Okay, so that part should be fine concept-wise. Now go to part B, where they tell you a neutron is moving in a straight line with momentum of p. The de Broglie wavelength associated with the neutron is lambda. On figure 10.2, sketch the variation with momentum P of the Dipole wavelength lambda. So this one is talking about something that is moving, has momentum P and has wavelength lambda. You know that you're talking about Dipole here. They already specifically mentioned to you Dipole wavelength. So you know it's lambda is equals to H over P. If H is constant, that would have meant that lambda is inversely proportional to P. Okay. So if you were to draw a graph of lambda versus P, you will get this. Both of these should be asymptotes. Okay? There's no intercept whatsoever. So when you draw a graph, it should look like this. It must not be shown to be touching the axis. Right? So that part should be fine.